Good afternoon, geometry students. I hope you are having a fantastic day. We are going to do notes for chapter 10 today. So section 10.1, chapter 10 is mainly about circles. And so today we're going to introduce some of the beginning vocabulary for the parts of a circle. And we're also going to talk about specifically segments and lines that intersect circles. So let's just start off by doing a very basic picture of a circle and labeling some of the parts. So I'm going to show the center of the circle with a capital letter C. And then I'm going to have a couple extra lines here. Let's have this point be A. And then we'll do another line over here with points B and E. You may need to pause for a minute and write these down. But we're going to use this to basically describe some of the key vocabulary for what a circle looks like. All right, so is there somebody who can look at that picture and come up with a radius? What would be an example of a radius? A radius is a segment whose endpoints are the center in any point on the circle. So one example of a radius might be, for example, CA. You could also say CB. That would be great. Now a chord also goes through the inside of the circle. It's a segment whose endpoints are on the circle. So for example, from B to F would be a chord because both of the endpoints are on the circle. From B to A would also be a chord. All right, a diameter, and I'm sure you've heard this word before, but a diameter is a chord that contains the center of the circle. So this chord right here is also a diameter because it goes through the center. A secant is a line that intersects the circle in 2 points. So for example, BE, line BE would be a secant. And then a tangent is a line that touches at 1 point. So line AE would be an example of a tangent. Now I know this is a lot of vocabulary, but we're going to be using all of this the rest of the chapter. Now I wanted to show you just a little mini picture here. Sometimes on the SAT exam, they'll ask you to find something called common tangents. So a common tangent would be a line that touches 2 circles at 1 point. So that would be an example of a common tangent. This would be an example of a common tangent, and then there would actually be 2 more common tangents. This line here and that line there. So we can have a tangent to 1 circle, and then we can have a common tangent that is there for more than 1. Now, there are 2 theorems that we're going to be using in the notes today. So let me do this better, THM. Theorem 10.1, and you never need to memorize the theorem numbers, says that a line is tangent to a circle if and only if it is perpendicular to the radius. Now, does anybody remember what the if and only if means? So basically, if it's a tangent, then it's perpendicular to the radius. If we say if and only if, remember, it means we can flip the order, and that's also true. So if the segment is perpendicular to the radius, then it's a tangent. So this theorem is true either direction, and that is actually theorem 10.1, but like I said, we don't need to memorize the theorem numbers. The other theorem from the section 10.2 says that if 2 segments from the same exterior point are tangent to a circle, then they are congruent. So if these segments are both tangent to a circle, then they are going to be congruent. Okay, all right, so now that we have some of the vocabulary and theorems out of the way, I wanted to do a few examples with you, and then we will do more examples when we go over your homework. So let's do example number 1. We're going to draw a picture here of a circle with a center at K. We have a point on the outside of the circle at L, and then another one at M. This length right here is 29, and the 29 does refer to the whole length of this side. And then this piece here is 20, and this is 21. All right, so the directions on this problem say KL is a radius of circle K. Determine whether LM is tangent to the circle. Justify your answer. Now remember, we learned that if LM is tangent to the circle, then it's going to be perpendicular to the radius. It's also true that if it's perpendicular to the radius, then it is a tangent of the circle. So if we can prove that these two lines are perpendicular, we can say that LM is a tangent. Does anyone have a thought as to how we could prove that those two lines are perpendicular? Well, we can use Pythag, because remember, we learned when we were talking about the converse of the Pythagorean theorem is if the Pythagorean theorem works, then you know you have a right triangle. So let's try doing Pythag. Let's see if 20 squared plus 21 squared is equal to 29 squared. 400 plus 441, we want to see, is that equal to 841? When we add everything up, we can see that indeed it is. So we know that triangle KLM is a right triangle since Pythag works. Therefore, we know that angle KLM is a right angle. And because of that, we can say that LM is a tangent. So that took a little bit of reasoning, but essentially we just needed to use Pythag. Okay, let's try another example here. Let's call this example number 2. In this example, we have another triangle that is included in our figure along with a circle. And this length is X, this is 16, this is 24, and this is also X. Keep in mind that the radii are always congruent. So this question asks us to find X. Now, in the figure, we also need to see that there is a right angle there. So this is basically a Pythagorean theorem problem. Now, the thing that makes this a little bit tricky is we need to notice that the hypotenuse here is going to be X plus 16. So to do Pythag, we would say X squared plus 24 squared equals X plus 16 squared. The first part's pretty straightforward. The square root of 24 is 576, but to do this part here, we need to FOIL. X plus 16 squared means X plus 16 times X plus 16. So we need to do the two first terms to get X squared, and then the outside to get 16X, the inside to get another 16X, and the two last terms to get 256. Now, fortunately for us, we can subtract X squared from each side. Remember, the subtraction property of equality tells us that we can subtract anything we want from both sides of an equation. We also have to combine these terms here. So we're going to have 576 equals 32x plus 256. When we subtract the 250x, we're going to get that 32x equals 320. And then when we divide by 32, we would get that x is 10. So on our figure here, this side is going to be 10, and this side is going to be 10 plus 16, which is 26. Notice that a 10, 24, 26 is a 5, 12, 13 triangle multiplied by 2. So that is one of our more common triangles that we tend to see. All right, I've got 2 more examples for you, and I'm so glad that you're watching the notes because you are going to get the most out of the class. Let's call this example number 3. On this question, the directions are to find x, and we can tell that the lines outside the circle are tangent to the circle because it shows that they are perpendicular to the radius. So because of that, the second theorem that we learned about at the beginning of our notes tells us that the lengths of the 2 tangent segments need to be congruent. So we can set them equal to each other and then just use our opposite operations to get that x is 5. All right, we're going to do one more example, example number 4, and then we will be done with our first notes for section 10.1. So example 4, this problem looks really intimidating, but it's actually not that bad once you've seen it a couple times. I do believe there's some problems like this on the homework, and so that's why I'm doing an example of this here. It might take you a while to label this figure, so if you need to pause your video, please feel free to go ahead and do that. This is obviously not being drawn to scale, but let's just go ahead and look at what we've got so far. The directions say to find the perimeter of triangle QRS, so the distance all the way around. Now, we have also been told that the circle is circumscribed within the triangle, which means that each of these pieces are tangent pieces. So these 2 pieces right here would have to be congruent. That section would have to be 2. Because this whole piece is 8 and this part is 2, that tells me that the other section has to be 6 so that they add up to 8. Now, because these 2 tangents have to be the same length, we know that this one is 6. And because these 2 have to be the same, we know that that one is 10. So this side is going to be a total of 12 units long. We already knew that this one was 8 units long. And this one is going to be 16 units long. So the perimeter is going to be 12 plus 8 plus 16. 12 plus 8 is 20, plus 16 more is 36. So that should cover pretty much every example, or most of the examples that you'll see in the homework. So thanks so much for listening and have a great day. Bye.